Okay, so this is the second lesson of my short course with an introduction to satellite antennas or antennas for spaceborne applications. In this second lesson I will cover in more details, having discussed some fundamental concepts about antennas in general. I remind you that we touched upon directivity, the definition of directive gain and directivity. We spoke about half-power beamwidths. We spoke about gain as different from directivity to some extent. We defined the patterns of an antenna. Now we would like to get into the actual application of antennas, specifically to satellite systems, and we'll also give some definitions, some basic configurations of antennas for satellite applications. So in the outline, is summarize the lesson. I will speak about the satellite antenna footprints, satellite orbits, because somehow the footprints depends on the satellite orbits. In particular, there is one important orbit for many satellite applications, is the geostationary orbit and constellation. We will describe the different type of antennas depending on the type of coverage you want to obtain, global coverage antennas, elliptic coverage antennas, or spot or multi-beam type of antennas, and also the so-called contoured coverage antennas or shaped beam antennas. We will just touch upon the beamforming networks, which are the networks needed for getting this contoured type of antennas, and we will introduce a very fundamental configuration for satellite application, that is parabolic reflector antennas in different type of architectures. At the end, we will speak also about phased array antennas and active array antennas that were just introduced in the previous lesson as an example of antennas where the reciprocity principle does not apply. So let's speak about the satellite antenna footprint. In the slide, you can see a satellite. It's not defined the orbit, and this satellite is radiating through its antenna, and you can imagine the pattern of the antenna that is somehow illuminating one part of the Earth, and this part of the Earth that is illuminated by the main beam of the antenna, and you can define a minimum gain by which the area is illuminated, is in fact called the footprint, antenna footprint, satellite antenna footprint. So in a satellite antenna footprint, in this slide is the example of a geostationary satellite. In particular, you see from the slide is the Hotbird, it's a family of Hotbird satellites, which are Eutelsat satellites. It's a very famous, used by many people to receive TV programs through satellite antennas. So this is the footprint of a specific family of satellites from geostationary orbit, but in general we can define, given the antenna footprint, the so-called isogain contour lines or lines. What are they? They are the locus of the places over the Earth where the gain of the antenna is the same. So we said that the isogain contours define areas where the satellite antenna is illuminating the Earth with the same directivity or gain. From the user point of view, and especially in case of a satellite for TV broadcasting, these contours over the Earth are expressed in terms of EIRP, that is the effective isotropic radiated power, it's a value in dB watts, or even in the corresponding needed diameter of the ground antenna that is necessary for a user to receive the signal, the TV signal, with a good signal over noise ratio. So in this case, you see that both values are given. So you see, for instance, that this type of antennas wanted to serve, let's say, to illuminate at best the European area, and in fact over this area you can effectively get a good value of, a very high value of EIRP, and conversely you can use a rather small reflector antenna on ground to receive the signal. So this gives an idea again of how good the antenna is on board and how good is the satellite illuminating the coverage area over the Earth, or the required coverage area. Of course, while the pattern of an antenna is the same, and it doesn't depend on the orbit, the intersection of this pattern with the Earth in terms of angular values, let's say the area expressed in terms of angles, depends on the satellite orbit. The farther away from the Earth the satellite is, and the smaller is the equivalent area in degrees of the pattern intersecting the Earth. So it is important then to consider the satellite orbit to understand what is the coverage over the Earth expressed in degrees. In fact, we should obtain maps of the Earth from different orbits, and they will correspond to the different angular spacing in degrees. There are several orbits for satellites, as you probably already know. One important orbit, which I already mentioned, is the geostationary orbit, where satellites are usually in a plane that is the same as the equatorial plane, and they fly around the Earth at approximately an altitude of 36,000 kilometers above the Earth. But there are then also low Earth orbits, where satellites are much closer to the Earth, in a range between 500 and 2,000 kilometers in altitude. There are medium Earth orbits that are in between the LEO orbits and the geostationary orbits, and there are several applications for MEO orbits. For instance, the navigation satellites like GPS or Galileo are in MEO orbits, medium Earth orbits. There are also the so-called highly elliptic orbits, HEO, which are characterized by the fact that the orbit itself is very elliptic. Remember that all orbits are elliptic by definition, because as they follow the Kepler laws, and the Kepler laws say that the orbits are elliptic, but the circular orbits are just a special case of elliptic orbits. So geostationary orbits are basically circular, while the highly elliptic orbits are normal, I would say, elliptic orbits, characterized by a perigee, that is the closest point of the orbit to the Earth, that is maybe around 500 kilometers, while the apogees are much higher, in the order of 50,000 kilometers or more. And this type of orbits have been used to illuminate, to cover well the areas of the Earth that are close to the poles. And so, for instance, in this class of orbits belong orbits developed by Russians, such as the Molniya and the Tundra type of orbits. So depending on the orbit, you will have the same antenna will have a different coverage in terms of degrees over the Earth. Let's look at the geostationary orbit, which is very important. The geostationary orbit, as we said, is a circular orbit. The radius of the orbit is in the order of 36,000 kilometers, counted from the surface of the Earth. So in fact, from the center of the Earth is around 42,000 kilometers. You have to add the radius of the Earth. What is the characteristic of the orbit? It is a very unique orbit. At that distance from the surface of the Earth, the period of rotation of the satellite around the Earth is 24 hours. So which means that the satellites move around the Earth, but also the Earth rotates in the same direction. The end result is that from a user on ground, it looks as if the satellite is not moving. He will always see the satellite above his head in the same direction. And this is very good for TV broadcasting, for instance, for all communications where you want to point a certain satellite and don't move, and you don't want to track the satellites and move the ground antenna to follow the satellites. All the antennas we use for the TV reception, for satellite TV broadcasting, are fixed. I mean, they are not following the satellite. This thanks to the geostationary orbit. Now, the geostationary orbit is a very important invention. It was never patented, and the inventor regretted not having patented this invention, and maybe not many people remember that the geostationary orbit was actually invented by Arthur Clarke. Arthur Clarke is a famous science fiction writer. He is the author of many famous novels, science fiction novels. One is very famous also because he's linked to one of the best, probably the best science fiction movie ever filmed so far, that is 2001 A Space Odyssey, that was directed by another genius, Stanley Kubrick. And this Arthur Clarke wrote a paper in 1945, so many years before the first satellite in 1957, the first Sputnik 1, and he was in fact proposing a geostationary orbit to allow satellite communication. So he was anticipating satellite communications where satellites had not been yet realized. And he was explaining that through the geostationary orbit and 3 satellites, a minimum of 3 satellites, equally spaced around the geostationary circle around the Earth, it was possible, in fact, to cover practically the whole of the Earth with fixed satellites that were not moving as with respect to the Earth's surface, and so allowing satellite communications all over the globe. So it's a very important invention, a very important constellation. In fact, used a lot. So this is taken as a first example to understand the concept of coverage from a geostationary orbit. So the first thing we could want to realize is a global coverage from a geostationary orbit. So we want to cover as much as possible of the Earth, having our satellite, as we said, at approximately 36,000 kilometers above the Earth's surface. So we see the geometry of the link, if you want. The Earth is seen, the full Earth, almost it, because you see that it cannot reach really the north and southern pole, but most of the Earth is seen from a geostationary satellite, from the geostationary orbit, under an angle of, total angle of approximately 18. As a matter of fact, it's a bit less, 17.5 degrees, okay? So if we want to cover that area, virtually possible area, with an antenna, we know by now, after the first lesson, that we will need a beamwidth of the same value. So in the first approximation, we should think of an antenna that has a beamwidth of approximately 18, 17.5 degrees. And this is what we see in the following slide, in the present slide. We see exactly the dimensioning of a global coverage antenna. This is the simplest antenna we can think of. It's still very much used in many applications, even for satellite communication. Is the antenna that realizes the maximum coverage over the Earth. We'll see that, in fact, we see here only the coverage in elevation, let's say north-south elevation. Of course, the same we should look, and we'll look at it in a minute, in azimuth. We said that we need 3 satellites, in fact, to cover the complete Earth. But in terms of beamwidth, we can take circular aperture, so it will be a completely symmetric type of beamwidth. We see it over one plane. The beamwidth, theta subscript 3 dB, the half-power beamwidth, we said it should be around 18 degrees, 17.5 to be very precise. So now, after the first lesson, we have the tools to dimension, let's say, to know what is the realizable gain from the antenna. We remember that we want the formula to get the half-power beamwidth as a function of the lambda, the frequency of operation, the wavelength of the antenna, and the linear dimension of the antenna. In this case, we consider a circular aperture, so the linear dimension is the diameter of the antenna itself. We can derive the gain from the same formula with a little simple transformation. We can consider an overall efficiency, including ohmic and radiated loss, let's say of 50%, 55%, which is a good and reasonable value. What we get if we consider a frequency of operation at 4 GHz, is a maximum obtainable gain in this geometry of the orbit of 20 dBs, which corresponds to a diameter of a circular aperture of 0.3 meters. So this would be what we call a horn antenna. It's a very simple feed. It doesn't even need a reflector. In fact, it's very small. With such a small feed, in fact, we can cover the complete 1/3, let's say, of the complete area surface of the Earth and get a 20 dBs gain, which is not a negligible gain. Of course, as we said, we need 3 satellites to cover most of the Earth. This is an example of Inmarsat satellites. Constellation of geostationary satellites are still very common. They are used by Inmarsat. Inmarsat is an international company, an organization that is devoted mainly to maritime type of communications, but other type of organization and companies such as Eutelsat, for instance, or SES Astra are also basing their business on geostationary satellites, and they have somehow the same type of coverage. We'll see that they have improved the coverage, but the basic coverage, if you really want to reach all places, in case of Inmarsat, even the sea areas are important because they are devoted to maritime communications. Then you need to cover with 3 global coverages, and these are 3 global coverages over the Earth. The antenna that is producing these, the 3 individual beams, is very similar to the antenna we saw before. There was an evolution, of course, from the very simple antenna realizing a global coverage that is shown in this picture on the left side. We wanted to get a better, higher gain. To get a higher gain, we know now the trick. The antennas are not producing energy, they are just concentrating energy. So if I want to get a higher gain, I have to reduce the area, the illuminated area. So if I get 20 dBs gain with a global coverage antenna, and I want to increase it, what I can think of is to divide the global coverage into 2. So I have 2 so-called EMI coverages, which means half coverages of the Earth, and there I gain some approximately 3 dBs because I have half the area to be illuminated. Or I can think of rather large spots shown in the 3rd picture in the slide, or even smaller spots. So I can get smaller and smaller spots. The smaller the spot, the higher is the gain. There are many complications in producing small spots. There are complications also from the system point of view in dealing with a multi-spot coverage. But what is the result? In the bottom of the slide we see the effect is that with a large beam that is covering all of the Earth, I need very large antennas because the gain of my satellite antenna is not that high, so my received signal will not be so good, and I need large reflectors, large antennas on ground to receive the signal. The smaller the area, the coverage area, so the smaller the beam width I can realize, and the smaller and smaller becomes the size of the user terminal. So much so that when I get very sophisticated multi-spot antennas with spot beams very small realized over the Earth, I can in fact even use very simple user receivers with very small antennas that are portable. There are communications today through satellites where I can use something that is very equivalent to a smartphone with a very small WIP antennas. This is achievable because of the gain I have realized from the satellite antenna, and the trick again is very simple, that I have to reduce the beam width, and this we'll see in a minute that means also increasing the size of the antenna. The antenna size flying today can reach very huge diameters, even more than 10 meters on board, but the reduction and the simplification is on ground. So this is the principle of how to size the coverage of an antenna to fit into the system and communication requirements. So if I want to now let's consider again, as a matter of example, a geostationary orbit, but it would not make it different if we consider a different orbit. I can think of a coverage of a certain area. In this case is a coverage of Europe as seen from a geostationary satellite, being very simple as possible. It's not global because I'm concentrating the energy over a specific area. So it is somehow a spot beam, a very large spot beam, but it is very simple. It is what we call an elliptic coverage. So it's the ellipse being the simplest shape I can get from an antenna. Circular or elliptic are very similar. It depends on the symmetry of the aperture on board that is creating the beam. So the elliptic coverage is the simplest coverage I can think of to illuminate a certain area of the Earth that I want to serve with my communication link. It can be generated on board by an elliptic aperture, ellipse being a general case for a spot beam or circular shape or elliptic shape. So in this case, the elliptic shape fits rather well. I want to, my coverage, I want to cover the European area, so I think of an ellipse that is oriented in such a way to cover it at best. The ellipse gives me some degrees of freedom, of course, but not that much. And I see that this coverage is not ideal. It fits well the coverage of the main part of Europe, but at the same time there is a lot of energy, I can notice, which is spread over the sea areas, the sea surface, and that is a wasted energy because I do not want to broadcast over the Mediterranean or over the North Sea. So there are better ways, let's say, to cover a certain area than an elliptic beam. Ellipses are also fitting into other coverages. For instance, an elliptical coverage fits well in covering the North America. So there were many satellite missions that were, in fact, using elliptical beams to cover the United States of America. And we see here an example of the coverage with the different realized EIRPs, the effective isotropic radiated power contour lines. If I want to further increase my gain, we said I have to go for smaller and smaller spot beams. And here in this slide we see how the spot beam coverage is realized. So I imagine I want to realize many such spot beams to cover my area of service. Then I have to think of, I introduce the concept of reflector antennas. We'll look at it in more detail in a few minutes. But let's say in this case I have a reflector antenna which is fed by several feeds that are illuminating the antenna. Each of the feeds is creating one individual beam. So this is a way to generate a spot beam coverage, a spot beam antenna. This type of coverages exist in practice, for instance, used for communications, even for TV broadcasting. When I want to serve at the best a country, a specific country, maybe also because that coverage is linked to a certain language. So imagine I want to broadcast TV channels over Spain or over Italy, over France. I may want to limit my coverage to that area where, by the way, the same language is used. And so in this case, I utilize multi-beam coverages. I need rather complex antennas, both on the reflector side, reflectors of relatively large size, and also array of feeds such that I can generate these different beams over the Earth. And but I can also want to realize shaped beams, so not only smaller beams, but beams that also follow best the shape of the area I want to serve. How can I get these shaped beams? Well, a very first simple way to realize the shaping is to shape the reflector of the antenna itself, so the aperture of the antenna. The elliptical reflector is a very simple example of shaping of the beam, because through the elliptic shape I get an ellipse, I can orient it, so it's very simple and not very effective, but still it's an example of shaping. Even better shaping I can get through the approach we saw before, to use apertures, reflectors, that are fed by several feeds. What is the idea? The idea is, shown in the slide, is that instead of having one single beam which has got a certain roll-off, so I cannot optimize the gain at the border of the area I want to cover, I can think of the combination of smaller individual beams that are added together in such a way that I can better shape, so I can better get uniform gain over the area I want to serve, and then a sharp roll-off over areas of the gain, over areas that I'm not interested in. The concept is maybe better expressed in the present slide. On the left side of the slide, we see the previously shown multi-spot approach, so an aperture, a reflector, fed by individual feeds. Each feed is carrying a different signal, so it is generating a different spot over the Earth. On the right side, I still have an array of feeds, but now the feeds are fed by the same signal, only combined in the appropriate way by a BFN, that stands for beam forming network. We'll look at them later in the presentation. So the end result is now a combination of the previous beams. I have a beam that is somehow the sum of the previous spot beams, so I can cover a larger area. It's important that the reflectors are the same size. In one case, I use the full size of the reflector to get several small beams. On the right side, I use a larger reflector to generate a wider beam, but with a much better shading. So I get a coverage that is larger than before, but with a better performance, better following the contours of the area I want to serve, at the expense of a larger aperture. I could have used a smaller aperture, but without any good shading, and at the expense also of a more complex feed network. So the same coverage I could have got with a simpler antenna, but with the worse performance. So this is the principle of what do I get out of a shaped beam antenna. Is a coverage similar to a previous slide, one slide that we saw before, introducing the isogain contours. And you see, again, is a coverage of Europe. You see here that the shading of the beam achieved a very good following of the areas that wanted to be served. Here there is an attempt to limit the gain, and so not to waste energy over, for instance, certain areas that are over the ocean, because the ocean is not of interest. Here the gain is concentrated in over Europe, over the north of Africa, because it was part of the coverage, and somehow you see that there was a calculated approach to optimize the gain where it was needed, directivity where it was needed. So this is the principle of contoured coverage.